All right, so we'll start chapter 2 right now. We'll keep ourselves on pace. And chapter 2 is significantly shorter than chapter 1. And this is where we're going to start building the foundation for functions, and more specifically, graphs of functions, which functions are what we encounter in chapter 3. And we also begin the study of graphs of the functions that we'll encounter. And then the rest of the course really spotlights particular types of functions along with their graphs. So we're going to build some skills in this section by examining two formulas that we can apply when 2 points are plotted in the coordinate plane. And obviously points are what make up graphs, and so this is something that we might have to do when we're presented the graph of a function or just an equation. An immediate application of these two formulas is when we study circles. All right, so the equation for a circle is actually based on the distance formula, and given any 2 points on a circle, provided that they're opposites from each other, the midpoint of them would help us find the center of the circle. So these formulas involve the geometry of graphs, which graphs are one of the major components of this course. After this, we will move on to section 2, not today, but section 2 looks at some more nitty-gritty things regarding graphs. We look at intercepts again and certain symmetries, and so we're really setting the table for what we're going to be doing later on with graphs of functions. So let's get to it. The first formula, the distance formula, is actually based on the Pythagorean theorem. And as you might know, the Pythagorean theorem gives us an equation that relates the side lengths of any right triangle. If we identify A and B as the length of 2 legs of a right triangle, then the sum of their squares, namely a squared plus b squared, equals what? Who can type it in the chat bar? C squared, yep. So if we square a and b, the lengths of the legs of the right triangle, it winds up. How does this relate to the distance formula? Well, first of all, the distance between 2 points in the coordinate plane is the length of the line segment that connects them. So there's a diagram below where I have 2 points plotted, and I don't have the points written out as ordered pairs, but rather I have the x and y coordinates of each of the points labeled on the x and y axis. So the first thing I'd like to do is just indicate the points in their ordered pair form. The point at the bottom of the line segment, I'm going to call that P1, and the point at the top I'm going to call P2. Now let's say P1 has the x coordinate of x1 and the y coordinate of y1, and P2 has the x coordinate of x2 and y coordinate of y2. The line segment that connects P1 and P2, its length is indicated by D, and as you can tell in the diagram, it's forming the hypotenuse of a right triangle. So the trick to figuring out this formula is to come up with expressions that give us the length of that leg of the right triangle and an expression that gives us the length of that part of the right triangle. And it's actually based on the x and y coordinates of the 2 points. Let's look at the x coordinates first. The first x coordinate that's on the x-axis is x1, the second is x2. The distance separating, or this chunk of the x-axis between x1 and x2, has the same length as this leg of the right triangle. Now the key to figuring out an expression that gives us the length of this chunk of the x-axis is to subtract the x-coordinates. And the order in which we subtract is important. Okay, to figure out that length, we start with x2 and we subtract x1. And I'm going to put that in parentheses. So the difference in the x-coordinates will give us the length of the bottom leg of the right triangle. Likewise, the difference of the y-coordinates would give us the length of the other leg of the right triangle. Okay, so that little section of the y-axis between y1 and y2 lines up with the length of that part of the right triangle. And as an expression, that would be given as y2 minus y1. Does that make sense so far? So, what does this all mean? Well, let me take this out of context and just make it a little cleaner looking. If this is D, this is x2 minus x1, and this is y2 minus y1, then we can relate all three of these expressions with the Pythagorean theorem. x2 minus x1 is like a special expression for A, y2 minus y1 is a special expression for B, and then D is just a replacement for the letter C. So if we do a squared plus b squared equals c squared, we can rewrite that as x2 minus x1 quantity squared plus y2 minus y1 quantity squared equals d squared. And what we're trying to find is a formula for D. But it's got a power of 2 on it. So we're going to get rid of that power of 2 to fully isolate D by taking the square root of each side. Okay, that cancels out the power of 2. And here comes the official formula, which gives us the distance. D equals the square root. Inside, we have x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And no, the square root doesn't distribute to cancel out the powers of 2, and that's because we have a plus sign in between the two sets of parentheses. All right, and this would definitely be one of those flashcard worthy formulas. You know, on one side of a 3x5, just write, the words distance formula, and on the back side of it, write out the formula, in its symbolic version, and add that to your, stack of flashcards if you've been making any. Now we will use that formula in an example, but before we do that, there's one more formula I'd like to derive, and that's a formula regarding a midpoint, which a midpoint is a point on a line segment that's halfway between the endpoints. And so I have another diagram here where we have a line segment. Let the very bottom point be P1, the very top point be P2, and the midpoint is exactly halfway between them, and I usually indicate that with the letter M. And the midpoint formula results in giving us an ordered pair. So when we ask you to apply the midpoint formula, we're actually really asking you to locate where the midpoint would be at. And in this ordered pair are going to be formulas which give you the x-coordinate of the midpoint and the y-coordinate. Now I'm going to drop a little dashed line segment down to the x-axis, and that little tick mark right there would represent the x-coordinate of the midpoint. And the way that we find that tick mark is by averaging the x values of the endpoints. And to average them, we add them up and divide by 2. Okay, that'll always give us the tick mark halfway between two other tick marks. We also average the y-coordinates to get the value of the tick mark that's halfway between y1 and y2. And so the midpoint formula, if you will, is given as an ordered pair where the first coordinate is found by averaging the x-coordinates of the P1 and P2 points, and then the y-coordinate is the average of the original y-coordinates of P1 and P2. And you guessed it, that's another flashcard-worthy formula. Okay, one side of it, just write the word midpoint, other side of it, write out the formula, and add it to your stack. Do you guys have any questions for me so far? Okay. All right, so let's do this example, and then it'll probably be about time for a break, and then we can move on to the rest of the agenda for today. This example, we're actually going to apply both formulas. First thing that we want to do is find the distance between the points P1 and P2. And here we have specific values of x1, y1, and so on and so forth. So it's always a good idea with problems like these to indicate what's going to be your x1 and y1 and what's going to be your x2 and y2. And I just go in order from left to right. So whatever coordinates come first, that's what I label as my x1, y1. And we do have a coordinate plane, so if you wanted to, you could go ahead and plot these points right now, which might not be a bad idea. The first point is -2, 5. Okay, that's P1. Next point is 4, -1. That's P2. And our answer to this first part will give us the exact length of that little green line segment. So let's do it. D equals square root quantity x2 minus x1 squared plus quantity y2 minus y1 squared. We'll go ahead and substitute. And there might be some extra parentheses that we use due to negative coordinates. So I'm going to actually change up and use brackets, because when I do x2 minus x1, I'll have to use some parentheses. It's 4 minus -2 quantity squared plus -1 minus 5 quantity squared. So once you sub in your values, you kind of want to work inside out. And here's what I mean. You'll start by simplifying the inside expressions in the brackets. 4 minus -2 winds up being +6 due to a double negative, plus, and -1 minus 5 is -6. Keep that in brackets or parentheses, whichever you're using, because when you square it, it should come out to be positive. Speaking of, we want to square next to get 36 plus 36 inside the square root. And we're almost there. The rest of the inside stuff that we need to do is adding the 36's together to get 72 inside the square root. And if this square root simplifies, which this one does, then you're going to see the simplified version in MyMathLab or on an exam instead of the square root of 72. And it does simplify because you can write that as 36 times 2 to get 6 radical 2. Okay, any questions about the solution to our first part? Okay, well, the second and final part to this is to find the midpoint, which I'm going to kick this off to you guys. All right, so refer to the formula on the last page and see if you can crank out the coordinates of the midpoint. And once you think you have them, go ahead and plot it to see if your answer makes sense. All right, I'll check in with you in a couple minutes. Okay, let's see how we did. X-coordinate of the midpoint is found by averaging -2 and 4. Okay, those are the x-coordinates of P1 and P2. Y-coordinates are found by averaging, well, the y-coordinate is found by averaging the y-coordinates. So 5 plus -1 all over 2. And that's going to be 2 over 2 for the x-coordinate, 4 over 2 for the y-coordinate. What do you guys feel about 1 comma 2? And there you have it. Now if you plot this point, and if you drew a perfect line segment, it should land on the line segment and also appear to be halfway between P1 and P2. The way you could verify that it's halfway between P1 and P2, or at least one way, is to maybe calculate the distance from P1 and M, maybe call that D1, and then move on to calculate the distance between M and P2, D2, I'll call it. And should 1, 2 be the official midpoint, then our calculation for D1 should equal the calculation for D2. All right. So I think right now will be a good time to take a break. I do have a recording of the solution to the very last example, so I think what I'll do is upload that into Blackboard.